Okay, so continuing on with our mole concept here. Okay, so what we're going to do, hopefully you're comfortable converting grams to moles, moles to number of atoms from the previous work. Okay, what we're going to do is just extend that to molecules. It's actually a very simple thing to do. Okay, think about a molecule for a second. Here's water, right? So what's inside a water molecule? An H, an H, an O. So what does one water molecule weigh? One molecule equals the mass of a hydrogen, the mass of an oxygen, and the mass of a hydrogen, which equals 1 AMU, and that's hydrogen, put that in there, plus 1 AMU, this is just from the periodic table, plus 16 AMU. So one molecule equals 18 AMU. Fantastic. Now if you remember what we did before, we said, hey, one atom of carbon weighed 12 AMU, right? What its components were in its nucleus. Same kind of thing with the molecule. It's just a bunch of atoms stuck together. So we can use that same concept. What works for atoms works for moles of atoms. What works for molecules on an individual level with AMUs works for moles. So 1 mole of H2O, add up the parts, they weigh 18, but 18 grams. Aha, so you have to make your own conversion factor. When you have a formula, just add up the numbers for the parts. Okay, if it's one molecule, it weighs 18 AMUs. If it's a mole of molecules, it weighs 18 grams. Okay, so very simply, remember the molecule is the sum of its parts. What works for atoms works for molecules. And we can summarize this, and you'll see this in the book a lot. We have an uppercase M italicized. That's molar mass, right? Or molecular weight, right? That is this conversion factor. So molecular weight, when we write it like this, of H2O equals 18 grams per mole. That's just the same information expressed in a more convenient way. Okay, if you like to think about it like this, it's a bit like density. So the density of water equals 1 gram per milliliter, right? Or you can say, hey, 1 gram of water equals 1 milliliter of water. So you can write a conversion factor in a slightly different way, which we've seen before. Okay, so this and this are the same information. I don't mind which one you use, but you'll see this a lot in the book, so it's really worth understanding what it means. Okay. Now, oftentimes you're asked to work out molecular weights. Okay, remember molecules are the sum of their parts. Very, very important, right? So have a periodic table next to you. You know, feel free to pause this and go and print one off, or look one up on your phone or something. Okay, just have it next to you, right? What we're going to work out is the molecular weight of CO2. I like to do it like this. A molecule is the sum of its parts. CO2 is made from a carbon plus an oxygen plus an oxygen. Hey, fair enough. What does carbon weigh? 12.01 AMUs per atom, 12.01 grams per mole, right? Oxygen weighs 16. Cool, we just won't worry about the units. 16. It's grams per mole, right? Add it all up, what do you get? 44.01 grams in 1 mole. Okay, you'll see that in the book. Something like that, but you can say, hey, 1 mole, let's bring this up. 1 mole CO2 equals 44.01 grams. So you can write it as a conversion factor or as the more kind of traditional identity, if you wish, or a molecular weight. Okay, now diphosphorus pentoxide's ionic. Phosphorus and oxygen. Actually, that's kind of in between, and we call it a molecule, right? Next one's ionic. Call it a molecule. So molecular weight P2O5. What I'm trying to say is what works for molecules also works for ions, which we'll do in a second. But P2O5. So if you like, 2 P's and 5 O's. So I'm doing a little bit of math here. 2 times phosphorus, which is 31 and change grams per mole, plus 5 times oxygen, which is 16. Run the numbers, 142 grams per mole. Okay, so we say, hey, molecular weight P2O5, 142 grams per mole, or I'll do it here, 1 mole P2O5 equals 142 grams. You can write it in either way. All right, if you've just been following along, great, try one yourself. Okay, so the molecular weight of calcium chloride, right? Calcium chloride is ionic, so that's a -1, that's a +2, so I need 2 of them. Careful, never forget, chemistry is very cumulative. What does that mean? It means what you learned before keeps coming back. Okay, so It's the calcium plus a chloride plus a chloride, which equals 40.1 plus 35.45 plus 35.45, 110 point change, right? Grams per mole. Okay. There we go. Molecular weight, CaCl2, 111 grams per mole. Okay, we actually need that for later because when we look at our calcium phosphate lab, that was the stuff we used. So we'll use this information later to solve a problem from our lab. Okay, hopefully that's making sense. Again, try this. There's lots of questions like this in the back of the book, and please feel comfortable with this before moving forward, okay, because it is a super important concept. All right, next one. Here's a worked example. This is just good for reference, okay? So if you ever want to impress your friends and relatives with this insignificant fact, you may, okay? So grams to moles to number of molecules, just like with atoms, grams to moles comes through now molecular weight, right? So instead of the box in the periodic table for atoms, now we work out our own conversion factor. 18 grams equals 1 mole for water, for example. So that's the only thing that's different. The first leg of the journey's the same grams to moles, but with a different conversion factor which you make from the formula, okay? And then, hey, the Avogadro is just the same. So we're going to go up and down this, I call this the spine, right? When we do a little kind of what I call the spider diagram later, we'll see that moles is really the center of all conversions. And as you can see, it's the center here. So we always go to or from moles, no matter the problem, okay? We might go from grams to moles to grams, moles to number of things to moles, or all the way through via moles, backwards and forwards, okay? And in this worked example, I've kind of done it in a two-step process just to show you a different way, but if you ever wanted, hey, how many molecules of sugar are in a standard packet of sugar? So if you're in a fast food place, obviously in your bandana or whatever, because you're doing the COVID thing. All right, so you're in the fast food place, you grab a packet of sugar. How many molecules are in there? So you're going to go grams to moles to number of molecules. It's going to be a big old number, right? So for this leg of the journey, okay, I'm going to do it stepwise. I'm going to do 2 steps. Get the answer, take it, and then convert it. You can do the whole chain like we did before, but this is just to show you a different way, okay? So obviously grams to moles through molecular weight. We need the molecular weight of sugar, and you can always get it from the formula, okay? So there's 6 carbons, 12 hydrogens, and 6 oxygens in that one molecule. A molecule is the sum of its parts. 6 carbons, 12 hydrogens, 6 oxygens. So a molecule weighs 180.2 AMUs, or a mole of molecules, i.e. molecular weight, 180.2 grams. We can write it as that. 1 mole C6H12O6 equals 180.2 grams. And you can use that as a standard conversion factor like we got here. And I recommend you do that when you set up a chain. Okay, so all we're going to do, first leg of the journey, grams to moles, 2.15 grams of sugar, 180.2 grams in 1 mole. So therefore, hey, makes sense. I got a little fraction of 180. I got 2.15 grams out of 180, so I got a small number of moles. Okay, so you know, if you were asked to work out the moles, that would be what you do. Okay, if you were asked to work out the number of molecules, which we have been in this question, you could just add on the next part and keep going, just like in the previous questions. But what I'm doing is I'm taking this as, because I know some of you like to do this kind of bit by bit. It's okay as long as you show the work, right? So take that answer. I got that many moles in my 2.15 grams. Now how many molecules? Well, it's that second leg of the journey from moles to number of molecules. You know, we prefer one longer chain, but if you want to do it piece by piece, you can, right? So take that answer. Okay, now remember the math has to make sense. You can't be adding stuff over here. You've got to take this answer. And hey, 1 mole is 6.02 times 10 to the 23 things. I get that many molecules. All right. So remember, you can't go directly grams to number of things. You've got to go through moles. You can do it stepwise, take the answer and work it again. Or you can do just like our previous examples. 2 links in the chain because there's 2 legs to the journey. Okay, hope that makes sense. Okay, that's a very important skill, converting grams to number of molecules, which we use all the time. Okay, now kind of a wrap up here in terms of concept. All right, so remember, formula weight, okay, although it's the same number, molar mass or molecular weight, the uppercase M we use, right? And then formula weight, same number. For example, for water it was 18, right? But it's 18 AMUs per one molecule, right? So if we use molecules, we like to say formula weight, 18 AMU equals one molecule. That's what we call formula weight, okay? But for molar mass, 18 grams equals 1 mole. It's the same number, just we're counting a mole, not a single molecule. All right. Now the cool thing is, if you remember a way ago, I said, hey, density is mass over volume, and that gave us that nice little triangle, right? Density is mass over volume, mass is density times volume, volume is mass over density. This is also a 3-variable problem. So I can say this, I can say, hey, molecular weight is grams per mole. Right? So molecular weight, if I had the grams and the moles for a sample, I just divide them out to get molecular weight. If I want grams, molecular weight times moles. This will really help us with conversions later, nice and quick. Moles, grams divided by molecular weight. So yeah, I mean, if you're not comfortable with the shortcut, feel free to just do a chain like we've been doing. But now, as long as you put the units in, they will cancel. So the next couple of examples, I'll do both just to show you how this kind of shortcut works. But nice little trick, you can do a triangle, just like with density, but with molecular weight. Okay. Don't forget the concepts. 1 mole is 6 times 10 to the 23 things. As we mentioned, formula weight and molecular weight have the same number, but different units. That's for a single atom in AMUs, or a single molecule in AMUs. That's for a mole in grams. Okay. And you can do the pyramid. Okay, I just mentioned that right there. Okay. So, interesting question. Why do you think this pyramid, this grams, molecular weight, and moles relationship is the most important, the most frequently used equation in chemistry? Think about what it does. It relates grams and moles via molecular weight, right? And you can always get that from the formula, right? So what can we do? We can go and weigh something, check. It's like the bag of pennies at the bank, if you remember our first part of the packet video. Go back and check that if you want, right? You can actually figure out the number of moles you can count by weighing, okay? So this allows us to weigh stuff on the balance. Did you ever wonder why we have a bunch of $2,000 balances in our lab? And I stand there and I'm really annoying and I stare at you when you weigh stuff because I know you're going to break the balances at some point. But it's a risk worth taking because this gives you the mass to a very, very large number of significant figures, like 3 decimal places, maybe 6 significant figures. If I've got the mass to 6 sig figs, that means I can work out the moles with this math to 6 sig figs. So the more accurately you weigh something, the more accurately you can count it. Okay, and that's exactly what we do in chemistry. We count things by weighing them. If we weigh them super accurate, we can count them super accurately. That makes sense. Okay, so that's why we have super good and expensive balances. All right, so let's use that and run with it. Now be careful. My advice is, read the question at least twice, make sure you know what we want, and then pull the trigger, okay? So if we look here, we have a bunch of questions, okay? A bunch of questions. And again, feel free to pause, right? Feel free to pause, but I'll go through them kind of slowly, all right? Okay. So, number of moles in 5 grams of oxygen gas, okay? So going from grams to moles. But be careful, it's oxygen gas, which is O2, okay? All right, so because it's a molecule, we've got to work out our own conversion factor. The molecular weight of O2 is 2 oxygen. 16 plus 16 is 32 grams per mole, or 1 mole O2 equals 32 grams. So you've got to be careful there, okay? So we need that conversion, grams to moles, for here. So I've got 5.0 grams of O2, take that over 1, times, how many grams? 32 grams is 1 mole. Grams cancels, 0.16 moles. Fantastic. So very similar to grams to moles for atoms, but we've made our own conversion factor. Should that have been oxygen atoms, it would have been a 16, right? 16 grams is 1 mole of oxygen atoms, but because it's a molecule with 2 passengers per car, it weighs twice as much. So we have to make our own conversion factor. Okay. Now P2O5, if you recall, okay, if I go back and show you, well, actually I'll just write down the number. For P2O5, I think it was 142, and feel free to flip back. It's 142 grams. 1 mole P2O5 equals 142 grams. Okay, we did that one before. Okay, this time we're going from moles to grams. Okay, so 2.5 moles P2O5 times, hey, 1 mole weighs 142. Flip back a couple of pages for that information. Okay, we worked out the molecular weight in the previous example. Work it through. What do we get? 355. It's a 355 grams. Okay. Cool. Sig figs, if you want to be like, really to sig figs, 3.6 times 10 to the 2 grams. All right. Yeah. All right. Next one, careful, number of water molecules in 330 grams of water. Interesting. I like this one on test. Hint, hint. Right. So if I got 330 grams of water, I got grams, I've got to go to moles, and then number of molecules, right? Grams to moles, we need the molecular weight of water, which was one we did, right? So water, 1 mole, 18 grams, right? And then, hey, Avogadro here. 1 mole is 6 times 10 to the 23. That's our journey, so let's cobble it together. So this one, unlike the sugar packet example, I'm going to cobble them all together at the same time. Okay, so I'm starting with 330 grams of water times grams on the bottom, 18 grams is 1 mole. That's this leg of the journey, isn't it? I use molecular weight to turn grams to moles. That's just like the first step in the sugar example, right? But I'm not pressing equals, I'm just doing it all at once, right? And then I'm going to do the second leg here. Well, 1 mole is 6.02 times 10 to the 23. It doesn't matter if it's molecules or atoms or bananas or horseshoes, whatever you're counting. Things, right? A mole of things is always 6.02 times 10 to the 23. Run it through, what do we get? 1.136 figs O times 10 to the, let's say 25 molecules. Don't forget number, unit, significant figures, always. Okay. This one, we're running that same scheme backwards, but we're going from number of molecules backwards to moles, backwards to grams. Okay, so we're going up and down that spine. Okay, remember that whole spine thing. All right, but the opposite direction. Okay, the opposite direction. So let's try it. Okay, actually a good place to pause if you want to really make sure you got this. Great place to pause, right? Okay, so we have 5.026 times 10 to the 24 molecules. Careful here, molecules have to go on the bottom. 6.02 times 10 to the 23 molecules, because we're doing this leg of the journey, is 1 mole. CO2. Hey, flip back, molecular weight of CO2 was 44. 1 mole, 44 grams. Knock it out before you check the answer. Just to make sure you get the same. 366 grams. Sig figs, 3.7 times 10 to the 2. Yeah, okay, but we'll kind of, for speed, we'll not concentrate too much on sig figs. Okay. All right, hopefully that makes sense. All right, now, here's a real fun thing. Okay, we're going to meet this in more detail later, but it's great to think about it now. Okay, what we've been doing is talking about relating the mole to other things. And that first thing we did was number of particles in grams, right? So you can count things by weight. Okay, turns out Avogadro, yeah, the same person, has another mole relationship, okay, and it's to do with gas. All right, now, Turns out when you look inside a gas at what's called a standard temperature and pressure, okay, basically at standard temperature and pressure, the gaps between the particles are the same distance. That's what standard temperature and pressure really means, okay. So if I had 1 mole of gas, I literally have 1 mole of gaps all of the same size. So that means collectively the gas will always occupy the same amount of space, because the space between particles is much, much, much bigger than the particle size themselves. So it doesn't matter how big the gas particles are, the space between them doesn't change based on their size, right? Okay, so because of that, we have a new relationship. If I just add up all the gaps between the particles in a mole of any old gas, I get the same number, and it's a conversion factor. So for gases, and it has to be a gas, all right, 1 mole any gas equals 22.4 liters. That's a nice little trick. Okay, that's a nice little trick. Okay, so a relationship between volume in liters and moles of gas, right? So here, use this information to determine the number of atoms of helium in a party balloon of this volume, right? So here's my party balloon. There's my party balloon, right? Okay, this has a volume of 35.6 liters. If I think about it, I can go with this relationship liters to moles, right? So this is my journey, liters to moles with my new relationship. And then, hey, moles is just a number. I can get number of atoms in this case. Helium, remember, is an inert gas. Oh, pull that up. Helium's an inert gas, therefore, it's an atom all the time, okay? So the number of atoms is the number of particles. All right, so let's run the numbers. Again, feel free to pause. 35.6 liters times 22.4 liters is 1 mole times 1 mole is 6.02 times 10 to the 23 atoms in this case, which equals, make sure I get the right number, 9.36657 times 10 to the 23 atoms. Oh, pull that up so you can see. All right, liters to moles, moles to number of atoms. There it is. Okay, now that's a nice little twist on moles, which will really help us later. Okay, in the next packet we'll start talking about gases in more detail. Okay, but it can be used as a conversion factor. And that brings me on to this, and this is a super important thing, okay? As you can see here, it's all about planning the journey. Wouldn't it be nice, and this is a super important concept, wouldn't it be nice if we were able to plan our journey real easily, right? Okay, and to do that, I'm going to give you kind of a route planner. Okay, so in the back of the packet, let's just flip all the way in the back, and I'm flipping to it. We're going to complete it later, but we're going to start what I call the spider diagram. Okay, now the spider diagram, it's literally the last page in the packet here. The spider diagram, which we'll fill in when we've done concentration, right? Because there's one more conversion. Bottom line is, I want you to think of a little spider body, right? There he is. And the spider's wearing a mole shirt, okay? Now, the spider, for whatever reason, only has 4 legs. All right, so there's 4 places you can go from moles, right? Okay, 4 places you can go from moles. Now think about that for a second. What was the first thing we did? To and from grams of a pure substance, right? Anything with a formula, right? Anything with a formula, if it's an atom, a mole of carbon weighs 12 grams. If it's a molecule, a mole of water, H plus O weighs 18 grams, okay? So I can use molecular weight or the box from the periodic table to figure out the grams, okay? So moles to grams, grams to moles, we've done that a lot, okay? And if you remember, hey, grams to moles, and then we could figure out the actual number of particles, and that's the same for everybody. Avogadro, right? Number of particles. Okay, number of particles, 1 mole, 6.02 times 10 to the 23 things. Okay, we did a lot of that. We went from grams to moles, moles to the number of particles. If you remember that lead example we finished off there, that was a good example. All right, so those are the two classics, okay, and we just learned one more. Okay, now be super careful. 1 mole of gas, this is only to do with the gas state, right, equals 22.4 liters at STP. So volume of a gas. It's the party balloon example we just did, okay? So we can use the relationship, and it must say STP. That means we've set the particle distance to a fixed number, essentially, meaning that 1 mole of gas occupies always the same volume at standard temperature and pressure. The example we just did with the party balloon, there we go. Later on, and keep this one ready to go later, we'll look at concentration volume relationships for a solution, which is always going to be aqueous. Okay, so volume is yet there, but it's going to be aqueous. So different volume, gas volume, solution volume. So that's something down the road. Okay, but, there we go. All right. So there's your little spider diagram, which is awesome. If you ever get stuck, sketch your spider and you can plan your journey. We did lots of grams to number of particles. We just did a volume to moles to number of particles. Okay, remember moles really is at the center of the chemist universe, isn't it? Okay, so if you ever get stuck, you're going to moles or from moles. Okay, that's the same for every single conversion. Okay, so we'll stop there. Hopefully that makes sense. Any questions, feel free to raise them in the discussion.